Alright everyone, we're once again talking about chemical equilibrium, and this time I'm actually going to show you several reactions described in your lab manual, and we're going to discuss what is happening and how we can apply Le Chatelier's principle to the changes in the reaction mixture's appearance that we observe. What I'd like you to do is have your data sheet handy so you can record observations as I'm doing these reactions. I would also like to point out that there are a total of 4 parts in this experiment. We're only doing first 3, and I'm also adding a little bit on to the third part, but we'll discuss detail when we get there. First part involves the equilibrium between what's called a chromate ion. It's ion whose formula is CrO4-2, and it happens to be yellow. So right here I have some potassium chromate in this test tube, and you can sort of see it's yellowish, a little bit with a green overtone to it, I would say. And the other ion that we're going to be looking at is called dichromate ion. It's a close relative of chromate. In that oxidation state of chromium, and both of these is +6. But most importantly, this one has 2 chromiums and 7 oxygens. It still has a charge of -2, and dichromate ion has a different color. It's actually orange. So it's easy to see how the changes in concentration of these ions are occurring because of the difference in their color. So the actual chemical equation of the reaction we're going to consider is what happens when we take chromate ion, something like this, and we add hydronium ion to our solution. And what's supposed to happen is addition of hydronium ion is supposed to create orange potassium chromate, or just dichromate or dichromate ion. I'd like to also, before we actually do these reactions, remind you that hydronium ion, whose formula is H3O+, is present in any aqueous solution of any acid. I use hydrochloric acid as an example here. So if HCl is dissolved in water, it dissociates and it produces hydronium ion and chloride ion. So hydronium ion is basically a marker for an acid. So first thing I'm going to do is I'm going to take this sample of potassium chromate, and I'm going to add, according to your directions, I'm looking at step 2 on page 120. I'm supposed to add 3 molar sulfuric acid, which I have here in this test tube. So sulfuric acid is H2SO4. It's also a strong acid. So I'm going to start adding just 1 drop of it. It basically recommends adding 1 drop at a time and stirring with a stirring rod. I do have a stirring rod here, but I'm just gonna sort of swirl it around. Right now you probably don't see much change, so 1 drop didn't change anything really. So let's see if 2nd drop will change anything. I don't know if you noticed, but when I first added that 2nd drop, solution did briefly turn a little bit orangish. Right now it's still yellow, so we're going to continue adding. So now I added about 4 drops total of sulfuric acid. And as you can see, the solution did turn pink. So what happened here? Well, let's take a look at this equation. What I started doing is I started adding more of a reactant, more of a hydronium ion, because remember, sulfuric acid is a strong acid. I actually wrote the equation of what happens with sulfuric acid in water, and you can see it does generate hydronium ion. So by adding sulfuric acid to my potassium chromate, I actually introduced more hydronium ion, an increased concentration of hydronium ion. In our original reaction here, hydronium ion is a reactant. So by adding sulfuric acid, I basically increased the concentration of a reactant. Now, what should happen to the equilibrium based on the Chevallier's principle when we're adding a reactant? Well, the system will want to counteract the stress by minimizing it. How can system minimize the stress of having extra hydronium ion? The answer is it can shift equilibrium to the right towards products, thus using up or reacting away any excess of hydronium ion that we introduced. So the fact that this solution has now turned orange suggests that equilibrium has shifted to the right, forward reaction sped up, creating more of orange dichromate ion at the expense of the reactants. So here is our dichromate solution. So now on step 3 on page 121, it directs us to start adding 1 mole sodium hydroxide, which I have right here. So this is 1 mole sodium hydroxide, and we're going to see what happens when we start adding. So we're going to go ahead and add 1 drop at a time, and then we'll discuss any changes that we notice and why those changes are happening. So I now add a total of about 6 drops of sodium hydroxide. My sodium hydroxide is less concentrated than my acid was, so it is taking a little bit more of it. So what are you guys seeing now? You're seeing the change that occurred from orange back to yellowish green. What do we think has happened here? Well, we think what happened here, according to our equation here, since color changed to yellow, it must mean that more chromate ion has now been produced. So what does it suggest in terms of our equilibrium? Well, it suggests that equilibrium has been shifted to the left towards the reactants, generating more of a chromate. So how can we explain this? Well, the explanation has to do with what happens when we started adding base, sodium hydroxide, which of course contains hydroxide ion, to our reaction mixture. One of our reactants originally was hydronium ion, but it's a well-known fact that hydroxide reacts with hydronium ion and produces water. This is your classic neutralization reaction, strong base, strong acid producing water. So what did we do by adding an AOH? We actually were able to reduce or diminish the concentration of hydronium ion in our original reaction mixture over here by adding hydroxide. So hydroxide here basically acts as I would usually say magic fishing stick. Imagine if you were able to reach into your solution and selectively remove a certain ion. So hydroxide allows us to fish out, if you will, hydronium ion. So we're removing hydronium ion. Let's take a look here. Hydronium ion is our reactant. And so hydronium ion being removed, it causes stress on the system. How can system compensate or minimize that stress of removal of a reactant? As we discussed previously, if a reactant is removed, the system will want to make more of it by shifting equilibrium to the left, so that forward reaction occurs faster, generating more of a reactant that we removed previously. And so in this case, the fact that our reaction mixture did turn back to yellow suggests that a reverse reaction sped up, shifting equilibrium to the left, generating more hydronium ion, and as a result also more of a yellow chromate. So this equilibrium here is illustrated by adding either strong acid and shifting equilibrium to the right, or adding strong base, removing the acid, and shifting equilibrium to the left.